Okay, NLP's recent success is partly due to large models pre-trained on massive unlabeled data, and then fine-tuned on specific tasks where a shared representation is used between multiple tasks. So the motivation for this project is that fine-tuning among multiple tasks can be very time-consuming, and there are no guidelines for selecting which tasks to train on per epoch of training. So in this project, we compared multiple methods for scheduling the training epochs. The data we're using comes from the GLUE benchmark. We're using 3 tasks: a sentiment classification task, a paraphrasing of the news task, and also Stanford question and answering task. All of these are cast as binary classification. So the evaluation metric we're using is the validation F1 score after each epoch of training for the sentiment classification or SST2 task. Our baseline is logistic regression with bag of words training, and we were able to achieve F1 score of 0.9. We also use a vanilla neural network with word embeddings trained from scratch. These are multi-layer perceptrons. We're also using BERT, which is pretty close to state-of-the-art and is pre-trained on unlabeled data. And we're using the uncased base BERT. There is a larger version, but this is still a pretty large model. So for training schedules, we're using round robin, which is just cycling between the different tasks per epoch, and also epsilon greedy, which is a banded approach with epsilon equals to 30.3, which means 30% of the time we're exploring and 70% of the time we're picking the task with the highest gain in F1 score. Okay, so here's our results. The training schedule, whether we use round robin or epsilon greedy, whether we use vanilla or BERT. The additional task we trained with, this is whether we use paraphrasing or question answering. What's really interesting here is BERT is able to, well, first of all, we're showing validation F1 score after 500 epochs, which is after early training, and also after 2,500 epochs, which most algorithms have actually plateaued in the training. And we're showing it for both training and validation. So in validation, the interesting result here is that for BERT with epsilon greedy, where the model is able to learn very fast, and it's the only combination that's able to beat our baseline. For future work, we want to expand this experiment suite to more tasks in the GLUE benchmark. We also want to experiment with other neural network architectures, hyperparameters, and using pre-trained embedding.